Hello, Ben. How are you?
Hey, I'm doing very well. How about yourself?
Good, good. So let's wait a couple of minutes. But in the meantime, if you want to
Hi, Ben.
sound check,
Hey, how you doing?
slide
Well,
check.
Sure thing.
Yeah, I will do a quick introduction and then we will start with your open lecture.
Yeah,
Sounds good.
if you want to share screen and try one time,
Sure.
I think it's perfect time now.
Can you see that okay?
Yeah,
Oh, good. How about that?
That's much better.
Awesome.
do you have video?
I do, but not, as part of the slides?
I mean, do you have video, audio in your videos? I think that's
No, that's
okay.
not. Yeah, it's
Okay,
just,
then
there's some like embedded GIFs, but that's it.
perfect. Then all good.
Excellent.
In the meantime, we have again quite a bit of attendees, so I would love to hear where everyone is joining today, from which city. Puerto Rico, New York, India, Berlin, Netherlands, Arizona, Finland, Bay Area, Uruguay, India, Canada, Sri Lanka, Washington, Dresden, Egypt, Seattle, UK, South Carolina, Virginia, Israel, Australia. Quite, again, diverse, especially for people from Australia. I guess it's quite a little bit late. Thanks for your commitment to our courses and our open lectures. 4:30 a.m. Carl. I hope you will get what you have invested for with your sleep. Exactly, it's definitely commitment.
Exactly, deserves an award.
So let's maybe show a few times the video and then we can start afterwards.
Maybe one more time and then I can start.
Exactly.
Great. Hello, everyone. Welcome to today's XR Pro open lecture. Let me share my screen. Okay. Yeah, as you know, as you've registered for it today, we are hosting an event series called XR Pro, where we invite successful and very renowned studios and XR developers to present and teach their lessons learned about several XR development topics. And just to explain a little bit more about our background, of XR Bootcamp's background, what we're always particularly proud of is our courses, of course, our 4 months XR Foundations and Prototyping Bootcamp, where the next one is actually starting next week. And in the end, you may have one of these very, very amazing careers. We've taken a few job titles, a few companies on the slide, where where our past students are working at now. And yeah, it always makes us very proud to see that our students, our graduates, are working in such very diverse and such very big companies as well. And there's 3 students which I want to highlight, Sadiq, Michael, and Emma. And especially Emma, she actually didn't have any coding knowledge before starting with us, the XR Foundations and Prototyping Bootcamp. And then she learned it with us, with our free C# coding course, which you can all sign up for if you're interested in learning C# coding. And now she is a technical artist at Polyarc. And you may have all heard of the VR game Moss, and Polyarc is the studio behind that. Very beautiful, very nice game. And yeah, so just to give you an overview about our XR Foundations and Prototyping Bootcamp, it's 4 months, and the free C# course, I would really encourage you all to take it. It's free, and you can basically see for yourself if you'd like to learn XR prototyping, because yeah, programming and coding is one of definitely the prerequisites which you need to to basically advance your career. And yeah, and you're learning Unity, you're really deepening your C# skills. And then at the core of our course is always the prototyping phase, the prototyping and MVP phases, where you're basically in each week creating one XR prototype. And then in the MVP phase, you will be matched with other students. You will work in a group in a simulated XR studio environment, get real briefs from industry companies, and work on different prototypes, which are very, very fully fledged MVP, like minimum viable products. And you're going to pitch them to these industry companies as well. And and for our industry partner companies, that's always the chance to get to know our students, to also maybe hire them after graduation. And and for us, it's very, very important that you learn together as a student group. You have a lot of live sessions. You're really working together as students. You can always ask questions 24/7 to all our mentors, so that you really get prototyping by yourself as soon as possible. Because obviously you can read all you want on the internet. You can watch all the videos you want on YouTube, and you can read books, of course, but nothing makes you learn better and more effectively than doing it yourself and trying yourself. And also like to get the encouragement and the accountability from different groups. Why it's actually really, really proven that cohort-based learning, cohort-based courses are the most effective way if you want to upskill fast. And that's why we basically as XR Bootcamp choose to teach that way, because we want results. We want you to get the return on investment on your course, on your time, on your investment into the course. And and one of our industry partners is Pearson. And Pearson is basically prototyping together with us, with our trainers, with our students. And for them, it's really a cool goal. They really want to create a language learning app. And we are all as XR Bootcamp, we are really happy that they are one of our partners, because creating language learning virtual reality games has been proven to be really fun exercise, fun task for all of our cohorts. And so there's definitely a lot of companies we are already working with, sending their developers to us. And we are always, if you're currently working in a company and you want to get your course tuition fee reimbursed, we can also help you with that. So if you need any assistance, asking your boss, asking your employer, getting course fees reimbursed, feel free to ask us for assistance. And please check our Trustpilot page. All our courses, all our alumni are very happy with us and give us always write us thank you letters and invite us nice reviews. And we're very happy and very proud that we can, we are always doing our best to make our students, get great careers and make them happy. So our trainers are always handpicked. We are making sure that our trainers are actually always working on their own XR projects. They're always having their own either XR studios or working at successful XR companies. And and maybe for this group here, we also have a rendering optimization masterclass. Maybe Ferhan, do you want to say a few words about that?
Yes, definitely. Thank you, Rahel. As Rahel mentioned, we are really handpicking our instructors based on the masterclass or boot camps that we are organizing. And this class is actually quite been on the market, and we were really happy to support many companies and many senior or intermediate level Unity and XR developers. The goal of this class is to teach you the most interesting and the well-known techniques in terms of Unity-based optimization and VR development-focused optimization. In the first 4 weeks, you are learning these techniques. And at the end of 4 weeks, we are providing a very nice, good-looking, high-quality scene running on Quest with 5 frames per second. So the goal is to actually bring it to the 90 frames per second in 2 weeks' time based on the techniques that you are learning. So today will be optimization day, and I would like to invite everyone here who would like to actually go towards the hands-on part, and we would love to also see you there. The class will start on May, so if you are interested, feel free to sign up. I will also post the link there. And we also have one rendering optimization checklist. It is also free checklist. So if you are interested, feel free to also take this 15 pages checklist, and then you can also even start benefiting from this optimization techniques by yourself. Yeah, for rendering optimization, I think we have.
There was just this one question, what is XR versus VR? So XR is just extended reality. It's like an umbrella term for augmented, mixed, and virtual reality. So yeah, virtual reality is just part of XR. Yeah, so I just want to invite, I hope you're all already there. I want to invite you to our Discord server, and hope that yeah, you will enjoy the open lecture starting now.
Exactly. So thank you, Rahel. Just one small maybe reminder. Right after this open lecture, we will have presentation and then Q&A. And afterwards, we will have an info session for those who are really curious about our courses. So our team will share the link of that course as well. It will be in a different Zoom link. So if you would like to also continue the discussion on the courses, feel free to join there. And we will have one more, actually just recently announced open lecture about ChatGPT. Our team will also put the link on the chat as well. So without further ado, I would like to invite Ben for his presentation. Just to give a little bit of maybe background information about Ben. He's from Owlchemy Labs. He has 25 years of programming experience, especially focusing on graphics and optimization. He worked on multiple platforms, including PC, console, mobile, VR, over the past 6 years. And he has helped all Owlchemy Labs VR titles as well, and many R&D projects. So I think we are right now really happy to have such an experienced veteran on optimization. So we are really looking forward to have you, Ben. For those who would like to ask questions, please use the Q&A tab under your Zoom screen, because this one will be the chance that we can see all the questions. If you are sending on chat, sometimes it may get lost. So I recommend that you directly ask on the Q&A tab. So again, thank you, Ben, and we would love to hear more about what Owlchemy is up to. And you have a new game recently released on Quest, right? Cosmonius High.
That's
and
right.
Probably you are now quite busy due to the launch at PlayStation VR 2. So we would love to also hear more about that, since you have actually perspective both from PC VR, console VR versus standalone mobile VR. So looking forward to hearing more.
Sure thing. Thanks, Farhan. So yes, this is achieving PCVR quality on mobile headsets. We have quite a lot to cover here. So a bit of a speed run, but if you see anything in particular that you're really interested in, definitely note it down, and we can hopefully talk about that afterwards.
Perfect. Stage is yours.
Hey, thank you. So yeah, as Farhan said, me, Ben Hopkins, I'm an expert graphics engineer at Owlchemy Labs. Been there for 6
We cannot
years
see
now.
your screen. I guess it's maybe you can re-share. So
Okay, let's do that. Can you see that now?
perfect.
Excellent. Okay, so yeah, Ben Hopkins, expert graphics engineer. I've been at Owlchemy for 6 years now. As Farhan mentioned, I've worked on all of our VR titles at Owlchemy. And that includes all of our internal ports for PlayStation VR and Quest 1 and 2. Been in this for 25 years. The first language was the AD assembler back on the Game Boy. Current languages primarily C# and HLSL, with a little bit of C++, Java, and Python for some of the kind of native plugins that we write on specific platforms for performance reasons, and then we do a lot of tooling and like research and development as well. So often jump into other languages for that, but generally during the day it's C# and HLSL. So a quick look at Owlchemy. We were founded in 2010. We've been VR focused, so exclusively making VR titles since 2016. We were acquired by Google in 2017. We make absurd and highly polished games. That's kind of our motives whenever we're working on a new game. And our motto is VR for everyone. So our games are Job Simulator, Rick and Morty Virtual Reality, Vacation Simulator, and Cosmonius High, which we released early last year. So a quick overview of the lecture. Mobile hardware is less powerful, fairly obvious. Mobile hardware has access to less access to most modern features, and VR is hard. We have a consistent FPS that's basically an immovable requirement. We can't really drop frames. We have things like reprojection that can kind of save us for a couple of frames, but we try and avoid that at all costs as well. So that's kind of like the last resort. And FPS is 90, maybe 72. Console gaming is only just now treating 60 FPS as like an expected feature. So having to always hit 90 is quite a tough challenge. And we have high resolutions greater than 1080p. And we also have to render everything twice per frame. But mobile hardware is still insanely powerful for what it is. I'm continually blown away at how powerful mobile hardware really is relative to some of the things that I've worked on in the past. And it still does have access to a lot of modern features, certainly relative to even a decade ago. And we use off-the-shelf engines, in our case Unity, which make things a lot easier. There's a lot of things we don't have to worry about in day-to-day dev because we use an off-the-shelf engine, but they're not necessarily built to be optimal by default. So that means that there's a lot of areas that we can optimize for. And this is kind of this is a good thing to keep in mind, that there's definitely lots of places that you can get performance back. So the first thing is testing on device. I really can't stress this enough. It's the reason this is the first slide. First off, using Quest Link is not testing on device. And I've run into a lot of people that aren't quite clear on this. When you're using Quest Link, you're essentially just running your game on desktop and then streaming video to the device. So it's still, for all intents and purposes, running on desktop. Playing an editor is really only useful for kind of quick sanity checks and general gameplay. So if you're working on gameplay and some issues that could arise from that, then working in the editor is fine. But generally, we prefer to test on device as often as possible. And things to consider, editor versus the device, you're using basically very, very different code paths of the engine runtime. Your shaders are being translated into a completely different language from what you're writing on in the case of Quest. And the graphics API features are completely different between the desktop you're running when you run it in editor versus on device. And obviously that's not even getting into the huge performance difference between your development PC versus the mobile hardware that powers the Quest. And this means that build times are important, a little bit of hyperbole, but almost as important as the actual performance of the game. So anything that you can reduce, anything you can do to reduce build time means that you can test on device faster, which is obviously great. Consider having a separate project for fast iteration on specific features. This is something that I do a lot if I'm, working on a very kind of focused, like shader optimizations or some new tech. I'll often have a separate project that is very slimmed down, because obviously, after a year to 3 years of development, you have a huge project. Even in the best case, it's going to take a long time to actually build that and run it on device. And iteration time is super important. And testing on device is super important. So having a separate project that you can work on specific features and really reduce that build time is a great thing. To give you an example, generally when I'm working this way, it takes 1, maybe 2 minutes from the time I hit build to being up and running on device, which, like I said, compared to even the best case of actually building the full game is night and day. So the first topic is draw calls. Quick overview: draw call is basically when you're asking the engine to render a mesh, and underneath the hood, the graphics API is rendering a mesh. This is considered a draw call, and it also comes down to the way that the graphics API is setting up state as well. So when you create a material and you have different properties, all of that has to be set up for each render, and that is basically a draw call. Internally, our target for a frame, so every time we render a frame, is less than 100 draw calls. And the less, the better. A lot of our scenes tend to err closer to 70 draw calls per frame rendered. And so this means that batching is vitally important. You can batch using various different techniques, multiple meshes into a single draw call. That means less draw calls than if you were rendering them each individually. And so the first one is static batching, and we use this for any non-moving geometry in the scene. So most of your level, if it's not being moved in any way, should be marked as static. And then you have dynamic batching. The limitation here is your meshes have to be 300 vertices or less. And the important caveat to that is you can only have 3 attributes per vertex. So for example, position, normal, and a texture coordinate. And then you have GPU instancing, which is great for reducing draw calls without the vertex count limitation of dynamic batching. And also there's a CPU cost to dynamic batching because it's actually creating that new batch on the CPU. Biggest restriction for all 3 of these approaches is you can't have different textures for the different original draw calls. So basically everything has to share the same texture if it's able to go into a batch. And some notes on some of this: static batching. Internally, we actually don't use the editor's automatic batching by just enabling a game object to be static and then letting the runtime batch. We actually use Unity's class static batching utility. This gives you a little bit more control over the way that things are statically batched. But the biggest thing for us is it also works around an issue where, for things to be statically batched automatically by setting their static flag in the editor, that game object has to be active on the first frame the scene is loaded. And for us, this is a problem because none of our game objects are actually active on the same frame that the scene is loaded, and I'll get to that a bit more later. And then for dynamic batching, something that I notice catches people quite a bit is the number of attributes per vertex is not actually related to the mesh asset. It's to do with the shader. So you could have a mesh that only has a position or only has a position in a normal, and you think that you're good. But if the shader that you're using to render that draw call declares that a vertex actually has 4 attributes, then you won't be able to dynamically batch that, even though the asset itself has the required number. And so optimizing texture atlases. As mentioned, you can't have multiple textures between batches. And so the more objects you can fit into a single texture, the more unique objects that you can batch and the more draw calls that you can reduce. And typically the way this is done is with basic rectangle packing. So if each of the input meshes uses its own individual texture, you can create a bigger texture and then just pack those unique textures into one. The problem with this is that tends to waste a lot of space. Unless every single one of those textures is very optimally packed, the chances are once you create an atlas, you're going to have a lot of space that isn't being used. And we wanted better than that. So we wrote a custom pipeline for creating our atlases. The way this works is within Unity, we can select a whole bunch of separate prefabs that we want to combine into a single atlas. Our code then generates an FBX file that basically has each of the renderers within each of those prefabs and the meshes that they use split out into a single FBX. And we can then basically bring this into Blender. And then we have another script that runs within Blender that generates a single combined UV unwrap for all of those objects as a whole. And for this, we use the plugin UV Packmaster, which is honestly one of the best packing tools that I've been able to find. It's super fast, and the way that it packs is incredibly efficient. To give you an example, the screenshot that you see on the right is, I think, 127 objects, and that's all packed into one space. And if you look closely, you can see there are things where you may have like a circle, and then it's able to figure out that there's a hole within that circle, so it can fit another thing within that, which is really great. And so once we've done that, finally, we export that FBX back out from Blender and bring that back into Unity. And what our code does is we now have the original UVs, and then we have the new UV set in the second channel. And so from that, we can read from the original texture and then write that out to a new texture. So essentially creating this brand new master texture that has all of the information for all of these objects packed into it. And since we're doing this all ourselves and using our own shaders, not only can we bake just the texture information, but potentially we can also include lighting and things in separate passes if we want. And so, yeah, as mentioned, the example here is the 127 unique objects all packed into a single texture. And a big part of this is because, as mentioned, it's not just doing kind of like a rectangular packing of the original UV layout, but it's actually taking the islands for all of the objects as a whole and really tightly packing them together. So in this case, we had a scene where we had multiple of each of these objects in the scene, and using the traditional atlasing approach, we were able to reduce draw calls from around 40 to just 3, which is a pretty great improvement. And the reason that it was 3 and not 1 is purely because we actually reached per batch vertex limits on Unity's side. So if Unity allowed for more vertices within a single batch, that draw call number could have actually been smaller. So improving batching with render queues. Draw order is dictated by renderer bounds and distance from the camera. So when Unity renders a frame, it basically is sorting all of the objects that should be rendered from front to back. And it also uses the bounding box of the renderer to factor into that, so that bigger objects will affect the order differently to smaller objects, for example. And then batching is dictated by this draw order, and then obviously the material compatibility that we've talked about. So if you have, and here's an example, if you have a whole bunch of object A that's close to the camera, and then you have object B, and then you have a whole bunch more of object A, these will actually be split into 3 draw calls, even if object A would be eligible for batching. And the reason for that is there's a clump of object A, so Unity says, okay, I can batch those. Then it finds object B, which won't batch, and then it'll find some more of object A. And so, yeah, you end up with 3 draw calls. So if you give either object A or object B's material an explicit render queue, this split will not happen. And the reason for that is, again, it's using the render queue essentially as another additional way of sorting when it renders the scene. So essentially what will happen is if you're saying, okay, I want object A to be in a render queue that's higher than object B, what's going to happen is first it'll see object B, then it'll see object A. There's nothing in between it spatially, and so all of object A will batch. And you'll save a draw call in that case. And so explicit render queues can have a really huge positive impact on batching in this regard, but also potentially a negative too. Because remember, we are essentially forcing the order that objects will be drawn in outside of the usual kind of back to front sorting that Unity does when it renders the scene. And so there's a possibility that while this may be efficient from one camera perspective, when the camera rotates a certain way, there's now a chance that actually it would be more efficient to split things up like this, pay for the extra draw call, but then make a saving for depth tests, for example. So it's always worth checking the way that your scene is being rendered from multiple different angles, using something like the Unity Frame Debugger or RenderDoc, just so that you're very aware that the changes you're making are giving you the biggest impacts. GPU instancing different meshes. So if you have several meshes that have somewhat similar topology, it's possible to store multiple vertex positions in UV. So this is a bit of a trick for getting around the fact that GPU instancing limits you to only doing multiples of the same mesh. So essentially what we're doing is we're taking two meshes, they have the same number of vertices, and we're storing the vertices of the second mesh in the UV channel of the first mesh. And so the actual mesh that ends up being rendered is basically controlled by a per instance property. So we can define a property in the shader that is updated for each instance within that single batch. And then that basically tells us whether to use the original positions or the positions that we've packed into the UVs. And so now we can have multiple different meshes that aren't restricted by the 300 vert dynamic batch limitation, still using only one draw call. And as mentioned, you basically just pick the appropriate positions, either the original positions or those that packed in the UV coordinates in the vertex shader, and then continue as you would with any other. And what's nice about this is you can even smoothly interpolate them. So you have, if you wanted to basically morph from one mesh to the other, you would just interpolate between, one position and another. And so this is an example that we shipped in Cosmonius. We had a whole bunch of these, they're called clicks, I think. They would float around the scene. They're fairly high density meshes, but they share basically the same topology. And so what we did is essentially pack each of these shapes into several UV channels. And then as mentioned, in the vertex shader, we can essentially just interpolate between each of the shapes. And so now all of these in the scene are basically taking one draw call. So textures, memory bandwidth is a major issue on Quest. This means do absolutely everything to minimize texture reads in your shaders. And just to be clear, multiple reads of the same texture can be just as costly as reading from different ones. So what I mean by that is you could have a material that has, say, 6 different textures you can assign to it, or you could have another one that just has one texture assigned to it. But within that shader, if you're reading from that one texture 6 times in different locations, that's essentially going to be the same cost as if you were reading from 6 different textures. So it's something to be very aware of. Another thing that you can do here that we also do a lot is packing grayscale textures into free channels. So if you have grayscale textures for noise or for masks or anything that you would use a grayscale texture for, and you have a free channel, most commonly it's the alpha, you can just pack that grayscale texture into that unused channel. And now when you read once from that texture, you're using different channels for different purposes. So taking the alpha one as an example, you may have just your regular texture that's just RGB, but you're not doing any kind of blending or anything. So you have alpha 3. And so you pack a grayscale texture into it, and now you just have to read from one location in the texture, and you can access that separate texture essentially for free. The other thing to be very aware of is that textures filtering mode has a cost. And this should be fairly self-explanatory. For point sampling, you only really need to read one bit of data from the texture. For bilinear filtering, however, you essentially need to get 4 pieces of data, because you're essentially taking 4 pixels and finding the interpolation of those 4 pixels to get the filtered output. And then with trilinear, it's 8 samples, because you're essentially doing a bilinear filter sample, but you're doing it from 2 different bitmaps and then interpolating the result of that. The other thing to be very aware of is that the bitmaps is super important. Not only do they help things look better, but they have a great impact on the cache hit rate. And what I mean by that is the GPU has a texture cache. So when you ask it to read from a specific texture, it'll store certain, like the positions you read from in a faster spot of memory. And so if you then ask it to read from those same spots, it'll be able to read a lot quicker if that same sample is already in the cache. And the reason the bitmaps help with this is because they're basically allowing the texture to fit more into the spatial use that you're using it for, i.e. an object that's farther away from the camera is going to use a lower bitmap level. That means it's a smaller texture. Therefore, the chances are that when you read from it, you're going to be reading from similar locations. And so the chances of that data already being in the cache is higher, so the read will be faster as a result. The other thing is texture compression has a huge impact on performance. We've done many tests of, without texture compression enabled on textures versus with it enabled, and it's a very big impact. Same with texture resolution, and this is somewhat related to the explanation for bitmaps, in that if you have a really large texture, the chances are that you're not actually sampling it efficiently. And so anytime that you're sampling from drastically different locations, the chances of you missing the cache are higher. And so therefore that texture read will probably end up being more costly than if it was a more appropriate resolution. And finally, avoid 3D textures at all costs. There are many reasons for this. Largely, it also comes down to similar to filtering, the number of samples that are actually needed behind the scenes is huge, and they just appear to not be very efficient on Quest. We've done a lot of work where we've wanted to use 3D textures, and the difference between an implementation that uses them versus one that doesn't has just been huge, to where we kind of just write them off altogether at this point. And so internally, our general strategy with textures, texture resolution is set individually to the lowest acceptable in the game. This means that we're constantly tweaking the resolution for the Quest side of our project per texture based on how that texture is used in the game. And this can change a lot, right? You can have an object that maybe at one point was super close to the player, but then through the act of development, at some point that object moved further away. So now it doesn't actually need to be as high resolution as it was prior. And so we keep an eye on this because it really does have a huge impact. We use ASTC compression, which is pretty much just a standard for Quest. And we use the largest block size that we can kind of live with from a visual standpoint. Some textures compress better than others. And so sometimes, it's just not acceptable kind of from a quality level, but it has a huge impact on performance. So we're constantly, just like with resolution, constantly tweaking to try and get the, that perfect balance between visual fidelity and performance from compression. As a general rule, our shaders are allowed a maximum of 2 texture reads in the pixel shader. 0 is very, very strongly preferred. And there are definitely exceptions to this. It's not like every single shader in all of our games are just only 2 textures. There are definitely plenty of examples that have more than that. But we have to justify the cost. And this is like a continual thing that you'll kind of come across in this talk is, there are always exceptions to the rule. It's just being very aware of what that exception is going to cost you, and if you think there's a benefit to your final vision. An example of that actually is that we tend to use trilinear in all cases, unless we absolutely can get away with that. As mentioned previously, trilinear filtering is going to be the most costly. But for us, the kind of hard stepping on head movements between different MIP levels that you get with bilinear filtering is just unacceptable visually. So we kind of eat the cost. The shaders, do as little as possible. It seems silly, but it really is kind of like the way to consider this. And I find particularly the simpler a shader is, the more chance there is for people to kind of justify it as well. We're not really doing a lot. So it's fine to just, add a simpler thing in here and not really think about it. But these instructions add up. And in particular, it's not uncommon for, something is introduced to the project. It may have been introduced with, 1 in 10. But then at some point, an artist found it and started using it for something else. And so you can never really be 100% sure that something is going to be used in the way that you intended. And so just trying to make sure that everything is as efficient as possible, in the case of shaders, as simple as possible, is really a good way to to go about it. Vectorize your math. Something that I see a lot is essentially doing the same operations on multiple individual values. So perhaps generating RGB, but literally doing each of those operations first on R, then on G, then on B. GPUs are built to vectorize. So pretty much everything that you can do in a shader will work on a vector. So if you ever find yourself with multiple operations that are essentially doing the same thing multiple times, try packing those values into a vector and then essentially doing those operations on the vector as opposed to individual scalars. And half precision, almost all of the things. So you can define whether a variable or a property is full precision float or half precision. On desktop, this is literally ignored. If you declare something as half precision, it will still be a full precision float on desktop. But on Quest, it's not. And this actually has a really large performance improvement. In fact, it's one of the first things that I kind of personally look for when I'm given shaders that may have been written by someone else we need to optimize. Just going through, changing everything to half, always has quite remarkable, in some cases, improvement to performance. And the exception to this is that with half precision comes less precision. And so for some things, this is just simply not usable. Larger texture coordinates, for example, you will start to notice artifacts caused by that lower precision. And obviously world space positions is another example that you really just can't get away with half precision. But most of the time you can, so definitely worth doing. And use keywords sparingly. So every keyword that you add to a shader drastically increases the number of variants that get generated once Unity compiles them. And particularly from a desktop perspective, there's kind of been a shift towards trying to make shaders that have a lot of features that can just be toggled on and off with keywords, which is great. But that number of variants has a huge impact on build times. To give you an example, not too long ago, I discovered a shader had been added to one of our projects that had over 20 keywords. And refactoring the shaders, just a few core shaders, because half of these keywords weren't even being used, with no keywords in each of these shaders, literally reduced build times for the project by 30 minutes, which is huge, and kind of goes back to the testing on device thing. It's difficult to expect people to test on device when their builds are taking potentially 45, 50 minutes at a time. And so being able to take 30 minutes off of the build time just by thinking a little better about how to split up shaders and not just throwing everything into a single shader with keywords is really super beneficial. And the other thing is and this is a little bit more in the weeds, but it's useful to get into the habit of viewing the code that Unity is actually generating for your platform from your HLSL shaders. Most often it is optimal. There's very smart people working on this, but sometimes it's not. And there have been cases that I've run into code that I would have expected to be generated a certain way that wasn't, and by actually kind of hand altering the way that I was doing things to try and massage Unity's generation into doing something better ended up being a win. And as a side note, it's kind of an old thing to be like, oh, don't ever blame the compiler. But just in this past year alone, I've actually discovered 3 reproducible bugs in the Unity shader compiler that were either just completely breaking builds, or were compiling okay, but doing things in a very wrong way. And with working with Unity, yes, it ended up being actually a bug in the shader compiler. So it does happen. The other thing is get to know the cost of the various intrinsic functions. This doesn't necessarily mean the exact cost, but over time, getting a feel for how certain intrinsic functions perform compared to others. And it's just a way of, when you look at a shader that you want to optimize, there are certain things you'll see that immediately stand out as being that this is something that is more costly. Is there a way I could replace this with a simpler approach? A perfect example of that is favoring simpler arithmetic over intrinsic functions where possible. And you can go in completely the opposite direction, obviously, and trying to handwrite everything yourself using just basic arithmetic will probably end up slower than using the intrinsic functions that are provided to you. But still, there are a lot of times where you can use approximations and just use simple arithmetic, and this will definitely be faster. For example, just as a kind of, again, more in the weeds, multiply and add is a single instruction. So there's a lot of things you can do with that. And many HLSL intrinsics actually get translated to inline GLSL by Unity, even when native GLSL intrinsics exist. And this kind of goes back to the becoming aware of the code that Unity is actually generating from your input shader. And a lot of the times this is actually an optimization on their part. They're aware that some of these chipsets, their native support for some of these intrinsics isn't actually as fast as the kind of the hand authored ones. But again, there have definitely been cases where I found that this isn't actually the case. So just another thing to kind of be aware of. And approximate, fake all of the things. We're working on mobile hardware and we're working on real-time games. Anything that you can do cheaper that looks good enough, that looks plausible, that's absolutely what you should be doing. And as a side note, Desmos.com is definitely a favorite tool of mine when I'm working on a whole host of shader tasks. It's basically an online graphing calculator, and it's super useful just for testing out different equations, trying to find approximate versions of like an equation that you may already be using. Are super useful. So transparency and blending is kind of my most hated thing. It is very costly on Quest, and we basically try and avoid and fake it as much as possible. Can break depth test optimizations. Even in the simplest case, you can think if you have an opaque object that's in front of something, potentially everything behind it is actually going to, it's occluded, the depth test is going to get rid of it, you're not going to pay that cost. If it's transparent, that's not the case. And where this can be less obvious to some people is, in the case of perhaps you have a sprite, and so that sprite is largely opaque, but has rounded corners or what have you. You are still paying the blending cost and all of the other costs for every pixel of that sprite, regardless of the fact that the majority of it is opaque. And multiple layers of blending for a single fragment can absolutely destroy you. We notice this the most with particle systems. As soon as you get to, maybe 4 or 5 layers of blending on a fragment, you start to see really, really bad performance. So yeah, be very careful with high particle spawn rates. This obviously ends up being a problem because, if you have a lot of particles spawning within a very short space at a time, the chances are there's going to be a huge number of them that are overlapping, which goes back to kind of like the multiple layers of blending issue that I mentioned. And another thing to be very careful of is alpha textures with large areas of completely transparent pixels. This has definitely bitten us a number of times over the years, to where we found out that there's a certain viewpoint in a certain scene where performance just absolutely tanks and no one's quite sure why. And then we start digging into it and we find that, an artist has wanted to create like a glow effect. And so they've essentially just created a quad that has, a tiny little kind of circle in the middle of it that fades out. And then the majority of the texture is completely transparent. And then they've layered multiple of those in one spot that are just kind of rotating over each other's. And so the visual effect is barely nothing. But you have, half of the screen being taken up by multiple layers of completely transparent pixels that, again, is still paying that blending cost. So that's something to be very aware of too. And it's possible to fake this using reflection probes, cube maps. This is something that we've definitely done in the past, and we're constantly looking to ways to employ this technique. So really all you're doing is you have an opaque object, you sample the cube map, the reflection probe, but instead of using a reflection vector as you normally would to get reflections, you essentially just use the view vector. And so that essentially gives you kind of approximation of what you'd be looking at through the scene. And so then you can use that to give the illusion of transparency on an object that's actually opaque. And particularly good for refractive surfaces, because they really help hide the fact that you're essentially just reading from a cube map. And so there's an example of this here. So this fluid stream is actually a completely opaque mesh, but it gives the illusion that you're seeing through it because we have a reflection probe set up in the scene. And yeah, as mentioned, we basically just sample from the view direction that gives us an approximation of the color behind it, and so that we can, make it look like it's transparent when actually it's a fully opaque object. So we'll talk about MSAA. MSAA ×4 is just the bottom line requirement for us on Quest. All kinds of aliasing are something that we're always trying to avoid on Quest. It has a huge impact on just visual fidelity. It's far from free on Quest though, and this is something that over the years I've heard a lot of confusion over. There seems to be a general idea that it's cheap or free on Quest. And the resolve part of MSAA is cheap, but rendering is definitely not. So a quick overview of how MSAA works will hopefully illustrate why this is the case. So MSAA can basically be thought of as an optimized version of supersampling. By supersampling, I mean you're essentially rendering at a much higher resolution and then shrinking that down to the resolution that you want. So in the case of MSAA ×4, you're essentially supersampling at 2 times, so twice the resolution. And so each screen pixel is subdivided into subpixels. So again, for MSAA ×4, each pixel would be divided into 4 subpixels. So if you look at the diagram on the right, you can see the big squares are an actual screen pixel, and then the 4 pixels within it are those subpixels. And so what happens is the depth test is actually performed at this higher resolution, but the pixel shader is still only called once per pixel per triangle. And so what happens is the pixel shader is called for the pixel, and then it copies that value that it gets back into whichever of the subpixels the triangle covers. Where this is a problem, of course, and this is how this works, is that obviously multiple triangles can potentially have coverage within a pixel along the edges. And so again, if you look at the diagram on the right, you can see the shared edge of those 2 triangles. We have pixels that have both green and red within them. And so what that means is, in this case, MSA times 4, for any of those pixels where there are multiple triangles covering them, you're basically paying for multiple pixel shader invocations. So it's still only 1 per triangle, but if we didn't have MSAA enabled, those shared edge pixels would only ever be calling the pixel shader once, whereas the ones that have green and red for times 4 MSAA, you'd actually be paying for 2 pixel shader invocations there. And so this is most costly with highly dense meshes, particularly as they move farther from the camera. And this can even be an issue with, fairly dense meshes once they get shrunk down. And this makes sense if you think about it, right? It's like the issue is the triangle edges, particularly the way that they cover these subpixels. If you shrink down a mesh when you render it, the chances are the edges are going to be covering up more of these subpixels than the center of the triangle that is completely covering a whole pixel. And this is actually one of the less obvious benefits to using LODs. If you're using LODs, then once an object gets far enough away from the camera, you're switching to a lower density mesh. And so one of the things that's actually going to fix for you is the issue that I'm describing here. And so I wrote a tool to kind of help teammates visualize and quantify this. So what this is displaying is basically the scene view with a kind of visualization of what I was describing on the previous slide. So any black pixel that you see here is just regular 1 pixel shader invocation. If you see a gray pixel, you're actually having 2 pixel shader invocations. If you see a yellow pixel, you're having 3 pixel shader invocations. And if you see a red pixel, you're actually paying for 4 pixel shader invocations in that case. And this is super useful for both validating LODs and identifying hotspots. We can just move around the scene view with this kind of visualization enabled, and it becomes very apparent when we're switching LODs if they are aggressive enough, or if perhaps we need to get the artist to actually remove more triangles and simplify them even more. And even prior to implementing LODs, it's a great case of being able to just quickly look at the scene. If we see that 50% of our rendered frame is yellow or red, then we know that that's an area that we can really improve on. Quick overview of how this works. Basically, it uses a custom shader. There's a semantic SV coverage that will actually tell you how much of a pixel is covered, or specifically those subpixels within the fragment shader. And so what this does is it renders the scene with the shader, records out this coverage information, and then visualizes it and actually uses a compute shader to give some metrics, so we can get a kind of rough percentage of the frame of how much was, the worst case, etc. A quick look at fixed foveated rendering. So FFR is really great on Quest 2. On Quest 1, we still used it, but kind of begrudgingly so. The artifacts that it introduced were pretty gnarly, to put it mildly. But on Quest 2, it's pretty great, to the point that when we actually first saw it, there were multiple times where people questioned if it was even on, because it was very, very difficult to tell just looking for kind of visual artifacts. That said, we still try to aim to only enable it in areas that we know are particularly hot. A good example of this is if we know that a secondary camera is going to be rendering in the scene. For example, several of our games have like handheld cameras you can pull out. So if we know that the user is using one of these cameras or it's looking at a particularly hot area, we can bump up the FFR temporarily while that's the case, and that will gain us some performance back to try and offset the extra work that we're doing. Something worth noting is that the amount that this will actually improve performance is directly related to how expensive your pixel shaders are. So if your game is only using, you know, an unlit shader that basically does nothing, FFR isn't really going to gain you any performance, because this is largely just a fill rate improvement. But for any game where you're doing anything of, you know, a fair amount of complexity in your pixel shaders, FFR can have a really huge impact on performance. So on the topic of secondary cameras, this is actually doable. We've had mirrors, monitors, handheld cameras, all kinds of things in all of our games. The first thing that we like to do is to decouple the frame rate. We don't need to be rendering our secondary camera at 90 frames a second. You know, 30 frames a second is fine and it's nicely divisible. So we'll just render the secondary camera every third frame, for example. And another thing that's super useful on top of that is being able to control like the cadence or phase of that render. So in the same way as, you know, each frame we can check, is this the, you know, the third frame, okay, render it. We can also look within that kind of 3 frame step and say we only want to render our secondary camera on the second frame of that kind of 3 frame interval. And where this is super useful is if you know that you're doing other heavy work and you're also employing a kind of time slicing approach with that work, you can offset it, right? So if you know that you're doing something every 3 frames and that's hitting on the first frame, then you probably don't want to also render your 30 FPS secondary camera on that same frame. So offsetting where that happens can be super useful for kind of smoothing out the workload. The other thing is decoupling LODs and culling. So we tend to render any secondary camera with more aggressive LOD settings and culling settings, fairly self-explanatory. And obviously favoring low resolutions is also an easy win. There's lots of in-world reasons you can explain this away, and this is, you know, this is kind of like another thing that we do a lot. Is it's not just finding optimizations, but it's finding, you know, ways that you can do things in a reduced way that kind of makes sense in the context of the world. So, you know, you can use simple shader effects such as monitor scan lines, etc., to kind of both hide and justify the lower resolution that you're rendering at. You know, an example, as I mentioned, we have like a handheld camera in some of our games, and this has, you know, the equivalent of like an LCD viewfinder on it. It kind of makes sense in the real world that that would be not high resolution. And just by adding a simple shader effect, it kind of further gets us away from it just looking like a lower resolution texture. Another super important thing that's worth noting, it's not advisable to call camera.render explicitly for your secondary camera, as what tends to happen is, particularly if you do this with an update, you'll end up stalling the GPU, and this will actually have a pretty nasty impact on performance. So instead, what we do is when we know that we're wanting to render a secondary camera on a specific frame, we enable the camera component in update. It gets to the end of the frame, Unity schedules that for rendering, and then in the following frame, we just disable the component. And just by doing this alone, we've noticed a huge impact on performance of the act of like rendering a secondary camera. So custom culling. For the types of games we make, built-in occlusion culling has never really worked out for us. every game we've kind of experimented with it again, and it's never really been a thing that's worked for us. At the resolution that we typically require, through profiling, the CPU cost of Umber on Quest is just like a net loss for us by quite a far margin as well. We can try and, bring down the resolution that the occlusion culling is working at, but then that brings in more issues. And so basically we handle all of our culling manually. We have a variety of specialized components that we've written over the years for doing this. And this definitely takes a lot more effort on the developer side, but it's essentially free to actually do it once it's running on device. So the effort is worth it. And one of the things is that due to the nature of our games, we already track quite a bit of information about all of the dynamic objects, of which there are a lot. And in particular, the containment of those dynamic objects. And what this means is it's actually fairly easy for us to essentially say all of the objects that are within a locker, disable the renderers once we know that the door of that locker is being closed, because we already have a lot of this information available to us. And by a similar token, it's also pretty easy for us to set up occlusion volumes. So, we know areas within the scene that the player can't view, so we can just set up a volume within that area, and then automatically any object that goes into it just has its renderer disabled. Essentially occlusion culling, but it's a lot more of a manual approach, but also cheaper, as mentioned. And we actually use a similar strategy, and in some cases, the exact same components to control logic updates as well, not just rendering. So we can basically disable components or whole game objects, which is super useful to also kind of trim the CPU workload outside of rendering for things that we know don't need to be updated based on their visibility. And aside from fully disabling, we also have a bunch of code that allows us to essentially update various components at a decoupled frequency from the frame rate. And so it's possible for us to also control the update frequency based on a similar culling logic, which is an even more kind of fine-grained way of controlling how much the CPU workload is. So with regards to LODs, similar to culling, we actually use our own custom system internally. This is mostly due to the fact that for some reason, Unity's built-in LOD system requires that the distance checks are from the main camera. And this is something that is just, it doesn't work for us. We have a lot of different cases where we want to control LODs based on some arbitrary point. And since we can't do that with the built-in system, we essentially had to roll our own. We've also experimented quite a bit, particularly recently, with screen space bounding boxes for LOD usage. So essentially, we can use either the bounds of the renderer itself, or essentially give an object kind of like proxy shapes. And then we calculate how big those would be in screen space, and then use that to control the LOD that's picked. And that can actually be a lot more efficient and reliable than just purely based on distance. A good example of that is you could have an object that's super small, that's very close to you, but then you manually scale it up. It's still the same distance, but it's now a lot larger in screen space. So yeah, that'd be an example of where opting for a more kind of screen space bounds approach would be beneficial. And so game objects can have multiple LOD levels. And for us, an LOD level can be either another game object entirely or a renderer. And essentially, we're just activating or enabling when the LOD level should change. We also have several components for generating LODs at runtime. So an example of this is we have one that can bake textures and light maps and stuff to vertex colors on demand. And what's really great about doing this, obviously we could do this offline, but being able to do this at runtime means it's possible to essentially test out different levels of detail and different settings without requiring a rebuild. So you can essentially trigger these things in a build on device instantly. So quick note on scene loading. In the past, we've required asynchronous additive loading of scenes without fading to black. So a good example of this was on the Rick and Morty game. We had portals. And so when a portal would appear, you could essentially see through it, see the scene that was on the other side of the portal, and you could actually step through the portal. And so there was never a fade to black. All of this happened instantaneously. And the way that we essentially implemented this was by each scene was its own scene, and then we'd essentially additively load the scene once a portal appears, do some rendering tricks to draw it, and when a player steps through it, we'd essentially teleport them instantly to that new scene. The issue with this is that it will always cause frame hitches. So asynchronously, additively loading a scene is going to hitch. However, what we discovered is this isn't actually the load. The load itself is happening on a separate thread and is not really that heavy. The problem is actually the await and on enable for hundreds, potentially thousands of game objects all coming into existence at once. All of the custom code that they're running, all of the instantiating that they may be doing, all of this stuff, that's really what kills you. And so the way our scenes have been laid out for pretty much all of our games since then is we have a single root game object that has the scene controller component on it. And one of the things that scene controller can do is basically takes a list of child game objects of that root game object, and those will all be deactivated automatically when the scene loads. And then it will essentially step through activating each of those game objects over some amount of time slice. Generally, we just have a 1 frame delay, but you could potentially have more if you needed a little bit more breathing room between frames. And yeah, these basically act as groups for various systems. So we will have our root game object in the scene that has a scene controller. Then 1 level down from that, it'll have several other kind of parent game objects for gameplay systems, different parts of the environment. And then within those game objects, they'll have all of the actual things that make that up. And then we basically would pass all of those kind of like parent game objects to the scene controller, and it automatically will time slice the activation on scene load. As a note on the implementation on that, it's actually possible to deactivate a game object that's being serialized in the scene as active without awaken on enable being called. This was kind of one of those things that tripped us up initially, as if you have a whole bunch of game objects in the scene, you load the scene, even if you on the first frame run through and deactivate all of them are still going to have awaken on enable called before you get time to deactivate or disable them. And so the way that this works is as long as a game object is a child of a deactivated parent, you can deactivate the game object within the deactivated parent, move that out of its parenting, and then reactivate it, and you will only get the awaken on enable called when you finally do intentionally activate it. And the same trick actually also works for instantiating. Using the instantiate method, you can actually pass in a parent. And so all of our scenes tend to have just this 1 empty game object that's deactivated. So when we instantiate an object that we want to control exactly when awaken or enable get called, we just pass in this deactivated game object as a parent to instantiate. It gets instantiated to a deactivated object. We can deactivate it then, and then carry on with our business, and all is good. So a quick note on profiling and performance in general, which is kind of largely what's been covered so far, but performance is a constant balancing act. And there aren't really any kind of, a lot of the things mentioned here is good general advice, but we want to push the hardware as much as we can. We have crazy ideas that we want to implement, And the way that you do that is by basically, making trade-offs. There are things that you will maybe do at a less precise value, or there are certain artifacts that you may live with because it gives you a little bit more performance to allow this, more impressive piece. And don't wait until the end to consider performance. This really should be something that you're thinking about at all times. Premature optimization is definitely a thing that can stifle creativity and prototyping, and it doesn't need to. It's not a case of never doing anything because you're concerned about performance. It's just constantly being aware of performance and keeping it in check and being aware of what you can do to make sure that it doesn't become an issue. And certainly waiting till the end of a project to do this is a lot more work than just being aware of it during development. And assume nothing. All of the things mentioned here, again, is kind of great general advice. It is generally true, but these are complex systems, and particularly on the GPU side of things, there's a lot of moving parts to where, in some cases, something that generally would be bad advice may actually be good in that very specific case. With the splat check system that we wrote for Cosmonius was a good example of that. There's a lot of things in that on paper don't make any sense, but each part just gives you just enough extra performance despite the trade-offs that when combined, it allows something a lot more impressive and complicated than should be achievable. So just quick example of tools that I use on at least a weekly basis: Unity Profiler, RenderDoc, OVR metrics, and the custom benchmarking framework that we use internally. And a quick note on that, basically what this does, it allows us to very quickly set up deterministic test scenes. They're not actually scenes, they're essentially just game objects in a list, but they act as scenes in a larger context. And so each test differs only in an aspect that we wish to benchmark. So essentially, all of these test scenes are identical, but there'll be one thing that changes, and that's essentially what we're trying to benchmark. And a perfect example of making sure that it's like for like, we disable head tracking completely. This is so that camera position and orientation are identical between tests. You can imagine if that wasn't the case, even if each scene contains the same mesh and the same shaders and all of this, if the camera is moving, the amount of screen space that may be taken up by that mesh is going to differ from test to test, and we don't want that. We want them to be as identical outside of the thing that we're actually trying to time. And so what happens is we do a build of our tests. They run on device. Each test will automatically run for a predetermined period of time. I think at the moment we default to it's like 4 or 5 seconds for each test. And then once it's done, it will just move on to the next one. And so for each frame, we use an API to get GPU metrics for the current test. And when all tests are complete, we average the metrics for each of those tests and write the results to a JSON file. And then in Editor, we can load this JSON file, which shows the results of the test as a simple chart. An example of this is shown on the right. And this is generally precise enough to evaluate lower level GPU functions, which is really nice and fairly rare. So as an example, in the one on the right, this is basically testing out the cost of the exact same mesh, but with bilinear, point, and trilinear for the way the textures are read for each of the tests, and then also using dependent and non-dependent UV coordinates. And it gives you a kind of a good insight into the way some of these things can affect performance, which when you're getting to the level of trying to trim 0.1, 0.2 milliseconds or something, when that's a big amount of time, this kind of level of granularity is super useful. And so load balancing CPU and GPU. OVR metrics, which is the overlay, if you're not aware, on Quest, that will basically show you a whole bunch of stats, mostly for the GPU, a little bit of CPU stuff, frame rate, etc. Really useful for being able to determine this at a glance. So apt is the amount of time taken on the GPU to render the frame in milliseconds. And you want this to be at least several milliseconds less than your total frame time. So at 90 FPS, we aim for an apt to be around 6 milliseconds. We definitely go above that, but that's kind of like, that's where we want to be as an average most of the time. And at 90 FPS, a frame is essentially 11 milliseconds. So if we're averaging 6 milliseconds, we have plenty of headroom there for if the player does something crazy, or we have a particularly difficult effect that we're going to introduce. And then CPU and GPU utilization will give you basically a percentage indication of how much work each are doing in that frame. And so by just using these few things, it's very easy to, look at the frame rate, look at the CPU and GPU utilization, look at how long the frame has taken to render on the GPU, and get a very quick idea of, am I more pressed on the CPU side or the GPU side? And so the point of this is that, if you're going through your game, or if you're in a particular part of your game, and you know that you're heavily CPU bound, then you clearly have space on the GPU. So is there stuff that you could be doing on the GPU instead of the CPU to kind of even that out a little bit? A great example of this is compute shaders. The Quest has support for compute shaders. We've used them quite a bit in the last couple of projects. And so if there's work that you could farm off to a compute shader so it's not as taxing on the CPU side, that is probably going to be a net win. Moving CPU controlled effects to shaders is another example. Things like particle systems, anything that the CPU is having to control. If there's a way that you could replicate that purely on the shader side, that's going to relieve some of that burden from the CPU. And conversely, if you're heavily GPU bound, consider work you could move to the CPU. So, runtime processing, optimizing data, meshes, things like that. If there's ways that you can make work easier on the GPU side by using some of that free CPU power, absolutely worth doing. And so here's a quick example of the former. So in Cosmonius, we have a splat system, which is basically where the player can paint all over every surface in the world. And we were very much constrained on the GPU side. And so what we ended up doing is on teleport, we would basically calculate an optimized mesh, a certain radius around the player. Shown here, the highlighted areas is the part of the world mesh that we want to split out. And so, yeah, on teleport, we do a whole bunch of kind of mesh calculation and optimization, and essentially produce like an optimal mesh that is only a certain distance around the player. And this basically means that we're rendering less triangles. We can now control the distance from the player that the pixel shader is being invoked at for rendering the splats. And so this is a good example of, we had some free power on the CPU side. So we used that to make the GPU side a little bit easier, because that was where we were more constrained at that point. And that's it. So thanks for listening.
Thank you, Ben, for this very long but very detailed presentation. I think, Ian, if you can make me host, I can also open the video, I guess. So Ian is with us, our advanced class mentor, and he's also into optimization. Hey, Ian.
Hello.
So we have quite a bit of number of questions. So when you are talking about different items, we have received a lot of questions. So what I suggest is, we have approximately, let's say, 30 minutes. Let's try to squeeze as many questions as possible, quick answers, or we can also guide to some tutorials or some like different maybe resources. I will hand over the question moderation to Ian. He will try to combine as much as he can Ben, feel free to also answer directly by typing. I think you can also see the Q&A part as well. But don't worry with the questions. We will ask to you as much as we can anyways. So verbally you can answer. For those who posted on the Q&A, we will try our best. Ian is our instructor, and he's also organizer of MIT Reality Hack that we were hacking with some Owlchemy Labs actually team there as well. They also joined, so it was quite nice in Boston. So nice to see you, Ian. And without further ado, I'd like to give you the stage and moderation of these questions.
Yeah, thank you for the introduction, and thank you, Ben, for such a there was a great detailed presentation about everything on the rendering side. So we have some great questions in here. Feel free to pick any that you see out of the batch that you think would be a great one to highlight. I'll also go through and select some that I think could be answered, that would be great to answer live. Sure. And also some of them, it seems like even it kind of came back through. So there was one in here talking about trying to balance the load between GPU and CPU of like by paying for a little bit more performance costs, but by doing some of those calculations, that mesh optimization, you're going to ease the burden on your GPU so that you can really squeeze as much performance as you can out of that XR2. Yep. Are there other instances that you like that's a great example, but are there other use cases where this proves to be very valuable?
Yeah, it's definitely one of those things. It's case by case basis, and what exactly we're doing that we can kind of work that in. On the trading CPU performance for GPU performance, anything where you can kind of control the amount of pixels that actually need to be shaded, or the amount of vertices that need to be shaded. It's a great place where if you have the power to spare on the CPU side, so you can actually particularly with meshes, generate some kind of optimized version of the mesh, do pre-calculations, for example. That's and I guess another more simple approach would be if you're doing a bunch of calculations in either the vertex or the pixel shader, and there's a way that you could actually calculate those on the CPU side and then pass them into the shader. That would probably be a simpler example of doing that, to where, yeah, you can basically trim down the amount of work you're doing in the shader side, and you're basically now just doing that on the CPU and passing it through as material properties or data that you pass through.
Okay, great. And then we had another question that was great, showing how you do your kind of standardized tests for performance to be able to have different passes where you're doing this very clear A/B testing. We had a question that was asking about using custom camera paths for position that move during the test. So is this you have maybe a spline that you're moving the camera along to see this is a test shot that you might do, or are you jumping cameras from different fixed points?
Yeah, so that's a great question, and that's something that we can totally do with these tests, because again, they're essentially just game objects, and the way that the test harness works is it knows that each of these game objects is considered a test. It deactivates them all. It activates one. Once it's run for X number of seconds, it deactivates, so reactivates another one. So literally anything that you want to do within that test, you can do. Most of the time when we've been using it's been for this super granular, comparing, an optimization that we're contemplating in a shader, taking the original shader, taking the shader with just that optimization in it, seeing the delta between them. But yeah, as having a scene and then essentially having a pre-controlled camera pass through it, that's absolutely something that you could do with this approach. And obviously what you could do is, if you wanted that kind of real world feedback of okay, the camera moves, along this path, and we want to test, doing that, but with a different material, or with a different shader, or with using a different compression setting on a texture or something. you could essentially just replay all of those tests, perhaps with camera movement, perhaps without. Yeah, completely within your control. It's pretty easy to set up, to be honest with you.
Mm. And then, well, all of the tooling makes it. I imagine you've probably built, or Owlchemy Labs has built quite the tool set in order to be able to test a lot of this. And you plugged a lot of other great resources like that UV Baker, which that was, is that on the Unity side or the Blender side?
That's on the, yeah, it's the Blender side. It's
okay.
It's last time I checked, so don't quote me on this, I think it was like $50. It's like a paid for Blender plugin. But yeah, it's really fantastic. Even outside of you know, what initially drew us to it, which was being able to make super optimized texture atlases, even just for general UV unwrapping, you know, for individual meshes, it's an incredible product.
That's fantastic. And people are also wondering, you gave maybe that's something that we can pull out from the slides or later, but you also showed a bunch of other really good resources, both within Unity for doing optimization and outside. There was another question here about, like, are there other tools that Owlchemy uses, that basically like looking for other resources that are either available for purchase or they're free tools that people just might not know of, but anything that you want to plug in that regard?
I would say probably the main one that's available that we use an awful lot is RenderDoc. For anyone that's not aware, RenderDoc, it can be thought of as similar to the frame debugger within Unity. It's just a much lower level version of that. It can run across multiple devices, multiple different graphics APIs, gives you insight into literally every aspect of a frame that's been rendered. I personally prefer that over frame debugger just because of the kind of level of information that it gives you and the accuracy compared to some of the ways that Unity presents its stuff in the frame debugger. Outside of that, the vast majority of tools that we use are custom internal ones, and this generally comes from very, you know, very discrete problems or things that we want to solve that there just isn't a good product that already exists for this. Either there are things that exist that don't quite do what we need or don't work well enough, or it just like straight up doesn't exist. Like the NSAA kind of visualization is a kind of good example of that. I've never really been able to find anything that actually shows that, and that was something that we noticed early on was having a pretty major impact on performance. So being able to, you know, go to like less technically minded folks and essentially be like, you know, black good, yellow, red bad, is super valuable.
Well, I guess in that way, it also speaks very much to the value of the studio, that you guys are solving new problems that might not have been considered, or things that are specific to you. This also ties into another question that we have on the board, which is about utilizing either some of the built-in tools like Shader Graph, or do you mostly work with doing your own custom HLSL or GLSL shader work?
So yeah, we are 100% handwritten HLSL. Some of our artists have started to get into using Shader Graph. One of the primary reasons that we actually don't use that is all of our projects are currently kind of in a version of Unity due to, you know, bug fixes and things like that, where Shader Graph isn't supported. On top of that, we also, you know, switching over to the like the custom render pipelines and stuff would be quite an overhaul to a lot of the setup for our existing projects. I personally prefer handwriting HLSL. That's just kind of the way that I am, and where I kind of started. But definitely, a lot of artists at least have been using it internally as a way of doing kind of look dev, and you know, they'll come to me and be like, here's, you know, this is kind of what I was thinking. How would you implement this in more kind of like handwritten optimized HLSL?
Awesome. I mean, it's quite the skill. Like I often, when I'm working with people who are very technical on the shader side, I often refer to them as shader wizards, because it can be a little bit outside of that domain where I'm much more used to being on the coding side. In that regard, we also have another question here that's asking about, do you have any recommendations for like a reading list of, are there good places to go for published papers, white papers, books, to get learning more about some of the subject material?
That is, that's one of those questions like get asked a lot, and I always wish I had like, what I'm currently reading as a list that I could send somewhere. Because I don't really have like a one-stop place I go to. I follow a lot of graphics engineers on Twitter, and so generally that's a fantastic way. They're always posting really interesting stuff, whether it's things they're working on themselves, talks that they've given, white papers that they're reading. So that's definitely a big one. And then generally the most that I end up reading is directly as a result of work. So if I'm working on a specific task on the shader side at work, pretty much the first thing I'm going to do is start researching, what is the current state of the art? What have people done in the past, so that I can hopefully not make the same mistakes, hopefully get inspired in some of the ways that other people have solved these problems. And usually as kind of a byproduct of that, you'll start going down the rabbit hole of I was looking for one particular thing, and then this paper referenced something else, and I start looking for that paper. So yeah, unfortunately, I don't have like a good kind of, this is a place that just lists all of them. Twitter is probably the closest I have to that, and then it's really just Googling what I'm currently researching at the time.
I mean, that's fair. I also pull a ton of inspiration from Twitter. There's lots of great game developers on there, as well as people doing graphics work kind of all over the different stack. And so you can get good resources, people sharing out free resources. I also see here in the chat, Austin shared a resource that I'm familiar with, is the Unity Shader Bible, is a book that was put out about working on shaders in Unity. And it makes a really good introduction to getting started on some of this work. Here, I'm going to look through our questions and see if there's another good one that we can surface. Do you have any in mind that you might want to pick?
I saw one here saying, do you recommend working with assembly references to speed up development? Yes. yes, I do. That has definitely been super helpful for us. We didn't always, but certainly I'm not sure if it was the last project that we started or the project before that, but yes, most of we have a pretty large framework that we built up over the years, and a lot of that has been split up into kind of sub-modules, each with their own assembly definition. So yes, definitely do that.
Awesome. And then there's still a ton of questions. What if we do a little bit of like rapid fire and we can run through some of these? So do you use Unity ECS or DOTS for any performance games in your projects?
We haven't yet. We have several people that are very, very interested, and they're kind of the ones at the company that are constantly pushing for it. Yes, we haven't used it in a shipping project yet, but it's definitely something that we want to a lot. The slight side to that, we have used a lot of burst compiler stuff. So particularly on the Cosmonius game that we released last year, we had a bunch of animation systems that we kind of rewrote to use like burst compiled job system, and that was a huge gain for us.
Yeah, there's lots of performance, but it's quite the undertaking to get into the DOTS stack.
Yep.
So is Owlchemy using OpenXR frameworks to streamline multi-platform development? Are you guys mostly on Quest? Or are you developing for other platforms as well?
So up until this point, we have been pretty much everything. So all desktop platforms, PSVR and Quest.
Yes.
And yeah, that's pretty much still the case.
Fantastic. And that's all OpenXR backend?
Yep.
Yep. All right. And then what is a visual element in Cosmonius High that you are the most proud of? Like, what was a very rewarding thing to get it working? You've definitely overcome some huge technical hurdles of like, can we pull this off visually, and finding a way to get there?
Yeah, I think from purely a combination of like visuals and the tech required, it's definitely the splat system, just because that was a huge undertaking. Going from, when we started, that was one of the games that we ended up porting towards the end of development. And so the going from the initial kind of getting it running on device to where we were maybe making 2 frames a second, to running all the way at frame rate, and kind of like what it took to get there, was, yeah, that's definitely something I'm proud of.
Fantastic. It was great to see the breakdown about how you accomplished that. Another question here. Do you have any thoughts or use cases for working with imposters?
Yeah, that is something that can help you in many, many different ways. The one thing that I would add to using them in general, particularly on Quest, kind of goes back to the issues with transparencies and blending. If you're going to be using like the more traditional, just flat kind of billboard style imposters, try and make them opaque. If you can find a way of either altering to where they are essentially geometric cutouts, or at least efficient in the sense that the majority of the sprite, the billboard, is opaque, and then it's just the areas where you need the transparency is kind of using a separate mesh that's the transparent parts. That'll definitely be super helpful for you, because that's kind of like the one area where it can bite you a little bit. It's obviously very dependent on how many imposters you have and exactly what they're like. But yes, if you end up essentially replacing all of your opaque meshes with transparents, you might end up in a not great place.
Okay. We also have another question here from Austin asking about, I didn't see anything discussing the depth buffer for near or far clipping. He's noticed that we have got better results on Z fighting and aliasing when we've increased the near clipping and reduced the far clipping planes to reduce the buffer distance being calculated. Have you seen something similar, or do you have any thoughts on that?
Yeah, that's a great one. Probably should have added that to the list. That is the bane of my existence when it comes to Quest. It's just a never-ending nightmare, and the primary reason for it, the far clip plane doesn't have as much of an impact, but the near clip plane absolutely does, and it's just due to the like floating point precision and the way that the depth buffer works. The problem is that we're a VR game, we're a very interaction-heavy VR game. You can pick up basically every single object. That means every single object the player can bring right up to their face. So we need a really, really fine-grained near clip plane. Otherwise, as soon as they bring it towards their face, you get the obvious camera clipping and all immersion is broken. So yes, Z fighting is just a never-ending nightmare for us. It usually, one of the things that you can do, it doesn't help a huge amount, but it definitely does give you some, is making sure that your scene is centered at the origin. So the area where the player can move around the most, make sure that that's actually 0, 0, 0 within your scene. That actually does have a fairly big impact. Outside of that, push the near clip plane as far ahead of the camera as you can get away with. But yeah, for VR games, generally you have to have it pretty close. That means that precision is going to go out the window, and yeah, Z fighting is just a nightmare. I mean, basically every single game that we've shipped on Quest has just been, some poor soul has had to go through and be like, this poster is, from this spot in the scene looking over here, this poster is Z fighting, and they have to push it forward. The other thing that we use a lot is the depth bias property. That's the other one of the alternative of actually moving the geometry itself. You can increase the depth bias. So basically what it does is it changes the depth value that's actually risen to the depth buffer without moving the geometry and where it's rendered, which is, it's basically the same thing as moving the geometry itself without moving the geometry. That still does, it's not a silver bullet. We still have plenty of areas. And so, yeah, it's just basically someone has to go through, and figure out all of the places where it's really egregious and fix it in one way or another.
Well, I thank goodness for quality assurance, I suppose, to go
Yeah.
through and do all those checks and
Yeah.
let us know.
Yeah. One thing I've actually, the top of the mind that I've been thinking of playing with recently is there is some potential to having your main camera have the near clip plane pushed, fairly far out, and then essentially having a secondary camera, which is generally very much inadvisable, but potentially only rendering using a very specific culling mask, just to catch the case of like, okay, we know a player is picking up an object or is putting their head close to a wall, we'll render this part in a second pass, perhaps. I'm still not convinced that the kind of performance trade-offs there would be worth it to, just the manual labor of having to go in and fix the side effects of the depth buffer issue, but it's definitely something I've contemplated. Maybe worth trying if anyone wants to try it.
Well, thanks for the recommendation. Maybe somebody will go and give that a test and let us know in the XR creator server how the results went. We have another question here from Dylan Smith, which is about, so do you think that alpha clip on opaque objects is better than transparency? We've heard that it can improve performance, but it also has the potential to break things on a tiled or mobile GPUs.
Yeah, so this actually kind of goes back to what I was talking about towards the end of how, some kind of common advice occasionally will work. So generally, I advise people not to discard, not to use clip in the fragment shader. And as you mentioned, like that is largely due to the fact that it breaks a whole bunch of optimizations on the GPU side on Quest. It basically, in the simplest terms, it's going to reduce some of the optimizations that could be done by the depth test. And so if your kind of goal is to alleviate the cost of blending, you're probably just going to be shooting yourself in the foot, and you may as well just use blending. The reason I bring this up as kind of like an exception to the rule is, again, on the splat text stuff, we actually did end up using clipping there for a very specific case where splats are essentially rendered as a second mesh over top of the world geometry. And the shading side of rendering the splats is super heavy. And we actually found in that case that using clip to discard fragments that essentially weren't part of a splat within that geometry did actually give us a performance boost in that case. But it's a very, very specific example. And the reasoning for that, I would imagine, is probably because we had very tight control over when things were rendered, the way things were being rendered. And so like any kind of effect that it had on like depth test optimizations was kind of reduced. And then the shader that we were clipping away was super heavy. So it kind of equaled itself out and actually ended up being a gain. General advice I would say is yes, if your goal is to increase performance of blending, i.e. using like clip discard instead of blending, just use blending, or even better, try not to have the transparencies in the first place.
Okay, yeah, thank you for the info. Dylan's also appreciates it. And actually there's another one here from Dylan that I was curious to know, is you were talking about the portal effect for Rick and Morty virtuality, and
Yep.
that's a super valuable thing because it's locomotion, like locomotion through virtual space doesn't always feel good inside of VR. And so being able to use these portal effects can have a huge advantage to be able to move the player from one space to another without actually having them move. So how could you speak more on how you handled the rendering for those portals? Are you using render textures? Are you doing it with like a stencil buffer?
No, yeah, so this was many, many years ago at this point, so I don't remember the exact, either we used a stencil buffer. I have a feeling we actually used some depth test tricks to where we essentially you had like a mesh volume that extended around the portal. Essentially very similar thing to using a stencil buffer, but I vaguely remember that we didn't actually use a stencil buffer. But yes, it was no render textures. It was all just we render one scene, we render another, and use some form of clipping to make sure that the other scene only shows through the portal geometry.
Okay. We have still a lot of questions and only so much time. Shall we? Some of them we could run down the list, but it also seems like some are, may have been answered from the presentation earlier. Any that, if you see any again that stand out to you, then feel free to jump in.
Sure.
Else I'll pick one to surface. So
is the 300 vert limit for dynamic batching per mesh, batch, or total? Yeah, so that's per mesh. So each mesh that can be dynamically batched has to be less than 300 verts, and 3 attributes is basically the limit there as well. So essentially 900 attributes per mesh. The total batching, the total vertex count per batch, I only was able to find out an answer for that when we ran into it on the example I gave, and so I don't know it off the top of my head. I want to say it was around 16,000, but I also believe that that may be per like platform dependent. I think they may actually change that based on what platform you're building for. So.
okay. We answered that one live. What are some of the algorithms you might utilize for yeah, there's some architecture questions in here too. Are there any algorithms that you use to handle your custom culling?
Not really, because as mentioned, like the culling that we do is pretty simple, and we err more on the side of like labor for free performance versus having a more automated approach that tries to do that algorithmically. So for us, yeah, it's very much a case of, you know, create in the case of kind of like occlusion volumes, we literally just create a trigger. We, you know, hook up a couple of components that say when things are in here. We know where the player is because we have the concept of kind of like play spaces and teleport zones. And so from that, we just know, okay, from this point, you can't see this specific occlusion volume. And so we hide those. The other examples I gave, you know, like we had lockers and doors and all kinds of things where objects could be like on the other side of them or contained within them. And that's a much more like systemic level thing to where those concepts kind of already exist in all of our gameplay systems. And so having components that just essentially tap into state and events for those systems and then just disable a list of renderers is very simple.
Okay, yeah, and I liked the implementation too of like just spreading out when you bring objects into the scene. Like earlier you had that scene manager of like we don't want to bring in 500 objects at once. We'll do that over 500 frames instead,
Yep.
just to ease the pain on that. There's another question here from Stomatus, which might be related, which is, do you use a kind of software architecture pattern to implement the whole game flow from start, initialize, end, reset? Having a dependency on Unity's awake and start methods isn't enough to give a full control state of the app. I don't know if that's within regards to like the rendering flow.
Yeah, I mean, in general, surprisingly not. I mean, we mostly rely on a lot of like the Unity kind of lifecycle events. We have our own like framework stuff for that, so that, for example, like as mentioned, we can like time slice specific updates. Like the cost of relying on a components update in itself has some overhead. So just as a result of that, we don't rely, you know, we tend to make sure that the majority of our components don't actually implement update. And we have our own form of update, which is actually controlled by like a manager. And so from that, it then becomes very easy to kind of give priority or say, okay, only call this update every X frames and stuff. But outside of that, as a general kind of architectural pattern, there really isn't a huge one. It's, you know, once you get into kind of like the more discrete systems and specific areas, absolutely, but that's also going to be very dependent on, you know, the needs of that specific system, the people that work on it. There isn't really kind of like an overarching set of patterns that we're like, this is the way that an Owlchemy game should be written on the code side.
We have another question here, which was about ANSIO filtering instead of trilinear filtering. Could you use ANSIO filtering instead of trilinear to avoid stepping between MIP levels? That might have been earlier when talking about MIP maps.
So in my experience, that doesn't actually solve that solves two different things. That's more having a better end visual result when filtering on like very steep kind of like grazing angles essentially. So your texture is still going to have to pick between bilinear or trilinear. It's just also going to have like the ANSO setting that will control that. So yeah, it doesn't really make a huge amount of difference. Like having bilinear filtering and then just bumping up the ANSO. I don't actually even know off the top of my head what we have that set to. That's one of those things that we've pretty much haven't touched, I think, since we first shipped a game on Quest. So yeah, I couldn't actually even give you like performance idea of that either. That's actually one that I've never even really looked into.
Okay, we also have some questions here that was it was really great information earlier talking about kind of the workflow of how do you get all of these objects batched into one call by like even like combining their textures down. We have another question that was here about, do you ever have difficulties with texture bleed because like everything is so closely mapped? And if so, like how do you manage not getting texture bleed on something that's so densely packed on that UV map?
So the way that we do that is pretty simple. On the kind of the UV packing side, the UV Pack Master plugin, I mentioned one of the many features it has is you can give a X number of pixels distance between islands that are packed. And then when we actually do the baking side of things back in Unity, as a secondary pass after baking all of the textures into that single texture, we then essentially do a dilation pass, which so essentially the texture is cleared to completely transparent. We bake all of the textures into their relative spots within that texture, and then we have a dilation shader that essentially just checks if a pixel is completely transparent or not, and if it's not, it essentially expands it out. And so if you look back at the image I shared of the example atlas, you'll see there's no gaps and you get this weird kind of everything's kind of smushed together. And that's due to the dilation pass. And that's specifically to avoid issues with texture bleeding. So as long as you have a big enough gap and you're dilating all of the things within it, generally that shouldn't be an issue.
Okay. And then looking at the time, it looks like we got about 5 minutes here, so maybe we should pick our maybe the last set of questions. I'll take a quick look and see if there's any that are particularly some good ones to pick, and if you have any, then feel free. We'll do our last 5 questions, we'll say.
Sure, sounds good. Best type of texture compression for mobile, at least for Quest, ASTC is that's the only one that you should be using. Do you ship mobile VR with compressed textures separate from PCVR? Or do you use the exact same size and resolution? No, so we definitely customize everything. So everything is tailored to the platform to try and get the best visual results to best performance that we can get for that platform. So yeah, definitely more powerful platforms will use less aggressive compression, use higher resolution, and we either use Unity's built-in like asset management tools for that, or as is the case with a lot of this stuff, we've kind of written our own tools over the years to make that a little bit easier to manage.
We have a question. Do you recommend working with assembly references to speed up development? Is that something that's commonly used on larger projects?
Oh yeah, so that was actually mentioned before. So yeah, we absolutely do. Yeah, we try and split. Our code base is pretty huge. We have a lot of frameworks that we've kind of built up over the years, and so a lot of that now is organized in a more kind of modular fashion with assembly definitions like within each of those modules to kind of make that aspect a little quicker. And it definitely does. That's been a huge component to reducing build times for sure.
A question here was about, is there a method for organizing and tracking the manual culling or activation of the meshes and game objects? Do you have an internal method for logging all these scenarios throughout the scenes and game progression? Or is it similar, like a technical storyboard? Is that tied into that, to the scene manager of earlier, of like controlling?
Yeah, so that kind of, we have a couple of different approaches to that, and that's definitely one of the areas where the kind of the effort involved starts to get definitely more so than if you had a more automated approach, just because there tends to be a lot of overlap there, to where we have, you know, gameplay and story systems that they may take control over something, and then we have like our culling systems, and it's definitely possible for there to be interactions between those that can lead to bugs. And that's often, especially towards, you know, towards the end of development, when things are getting a little bit more difficult, things get missed, people make changes, and so that's definitely an area that can be a little bit more problematic. Is, yeah, you have a lot of these kind of like interworking systems that can kind of clobber over each other if you're not careful, or you set something up wrongly.
Okay. All right, I think last three. Here, if there's any that you want to pick or knock out. I have one that I'll save probably for the last one.
Okay. I see someone asked, do we avoid using transparencies altogether, or are there specific techniques we use to fade them? So again, no, like we absolutely, like a lot of these things, you know, there's a lot of examples, particularly within the talk, where it's kind of like, this is very bad and we avoid this at all costs. And it's very true. As a general rule, we do. But no, we don't completely just, there's almost nothing that we ever say like, no, we 100% don't do that. And with transparency is a good example of that, because it's, for one, it's just not realistic to completely nix them with the kind of games and art that we make. So it's more just, again, much like with the recommendation of number of texture reads and shaders, it's kind of a rule that we try and like enforce as much as possible. So just so it keeps people, you know, at the top of their mind that this is something that has a very real cost. Is there a way that I could be doing this differently? Is this something that we could fix in the design phase before we even get to actually building assets and tech for it? We have plenty of transparency in our games. It's just one of those things that can very quickly kind of balloon out of control. And so, you know, hammering home that this is very costly and can be very, very bad if you start to just put too much of it in the wrong combination. It's definitely one of the top things that we always try and impress on new people, is like, be very careful with transparencies. If there's a way that we cannot do that, we would prefer that. But we absolutely have, you know, lots of particle effects. We have windows, we have glass objects. We just try and control it as much as possible.
Okay. And for with the time that we have left, I think I'll have this one last one, which is somebody was asking about if there's people whose their primary role is optimizing XR content to be able to get it to render and stream quickly, exactly like the skill set of yourself. And so as like with XR Bootcamp, we're very interested in creating a community of people that are learning about it. And so any other resources about, like, how would you describe that role? And then do you know where, you earlier mentioned Twitter, other places that people with that same skill set might be hanging out, sharing their work, looking for work? I mean, I'm also looking to find good shader wizards and rendering optimization specialists for my own hire. So do you have any thoughts on where people are, where is that scene currently taking place?
Yeah, so that is absolutely a job in itself. You know, depending on the size of the company, depending on the kind of like work that they're doing, it may be a very, very specific job title where that's all you do. It may be, you know, you're wearing many hats and that's something you specialize in. Generally, it would be graphics engineer would probably be like the primary title for someone that's focusing on that. Optimization engineer is another one that I've heard. But then even down to, you know, tech artists are that kind of middle ground to where they're a lot more on the art side, but they also should be very technically competent. And they should definitely be aware of the cost that the things that they're making is going to incur. And that's, you know, something that they're more aware of. And it may be at certain studios, it's more on the tech art side to optimize and make sure things run quickly. So yeah, absolutely a job title, can fall under multiple different umbrellas. As far as like where we hang out, Twitter, Reddit, just email. Like I've over the years have, you know, watched a video of someone that I thought was super interesting or was presenting a topic in a super unique way, found their information, emailed them. We tend to be fairly respondent to that in my experience. I don't think I've ever emailed someone like that out of the blue and they've been anything but super happy to talk to you about that stuff, because we will generally love to talk shop. And then outside of that, you know, conferences, game jams, all of those kind of things. Anywhere where you're going to find kind of game devs, you'll probably find a few of us.
Fantastic. Well, thank you, Ben, so much for your time and coming to talk with us about this and sharing so much of that great knowledge. And thank you everybody for your questions. I hope that everybody got to learn a little bit more and walk away with a greater understanding, as well as some next steps. If you're interested in this kind of work, if that's something that you want to be a part of, then feel free to get into those communities. Maybe shoot Ben an email.
Yeah, please do.
And then also we have at XR Bootcamp, we have our rendering optimization course that is also available if you want to learn more directly with us. So, and yes, thank you everybody for coming and thank you for your time.
Sounds great. Thanks, Ian.
Thank you.
Thanks,
Have a good
everyone.
day.
Bye.